Okay, so this is assuming that everything works out great. All right. So what we're going to cover now is going to be chapter 2.3, instantaneous rate of change. So what we'll do is we'll go over it conceptually, applicatively, appli and I guess like vibes. Okay. So first, definition of the instantaneous rate of change. Okay. The instantaneous rate of change is going to be defined as rate of change of some function f of x at point x equals a. There's two ways you can go about it. One, the limit as h approaches 0 of f of a plus h. In this case, you're using x equals a, right? And so you're taking that approximation like we talked about in the previous video, minus f of a, the whole thing over h, and it's this limit of this whole guy, okay? Whole thing, that's just part of it. Alternatively, f prime a. They're the same thing, okay? That's it. That's the instantaneous rate of change. You can either derive first and then plug a in, or you can do it directly here. I prefer deriving first and then plugging a in, only because now you have a formula that you can hold on to if you need it for later. Yeah, that's it. Here's some derivative notations. So the derivative of f of x can be written as f prime of x, which is going to also be the same as f prime if there's no other functions and stuff like that. You can also write it as y prime. You can also write it as df dx. So the derivative of f relative to the change in x, right? That's why we used to use a delta y delta x notation, change in y over change in x. So the change in y over the change in x, which can also be written as dy dx. Again, the change in y with respect to the change in x, which is just slope. Fancy. And if you want the instantaneous rate of change form, you can write it as f prime a. You can write it as y prime at x equals a. You can write it as df dx at x equals a, or you can write it as dy dx at x equals a. All are valid, all are okay. So the application is going to be as follows. So let's say that you have actually, how many of you have taken physics, right? If you've taken physics, you'll understand that once a object is thrown in space, right, it'll go like this and it'll come back down, right? So suppose you do that, right? But let's say this is like a rocket, right? It goes up, whee, stops, and it comes back down, right? Okay. Now let's say that at let's say right here, right? At this point right here, your rocket, I'm gonna do my absolute best to draw a rocket. Right? It launches, and at this point, it releases, I don't know, it breaks off and it launches some other thing, right? It launches, I don't know, a parachute, right? You might want to know, let's say the parachute looks like this, right? and I don't know, on the parachute is like a box. Sure, why not, right? The key here is at the point of the parachute getting released right here, right? You're gonna want to know how fast that thing is moving because up until that point, it is moving the same speed as that rocket, right? And once you know how fast it's going, you can start doing things like, oh, well, if my parachute's here and I know the speed, then I know what it'll do when it falls down here, right? You're gonna want, you want the velocity of the rocket here, right? So, big picture, right? What you can do is you can say one, or for a tangent line, right? Which is defined as a line with the same slope as a curve that also shares the point. Some linearization. My personal favorite is this situation. Okay. So basically, all you have to do is one, get a point. You don't even need a full point, get an x value. Two, find f prime x. Three, plug in, let's say like x equals a, right? A into f prime x, which will give you f prime a. Now you see the vision now, huh? And then find y value for f of x at x equals a. So basically you're looking at f of a, f normal, okay? F normal, not f prime, okay? And so now you have the slope because of this, right? And you have point, and you're not ready for this. Oh, and the point is going to come from, this is your y value, and this is your x value, right? You have slope and a point. I sure hope you know how to put a function into point slope form, because then all you got to do is say, oh, y minus f of a is equal to f prime of a, because that's your slope, times x minus a, right? Because this is the same form as, let's use a different color, huh? Y minus y1 is equal to mx minus x1. Magical. That's it. That's how you find tangent lines. I don't know why I had such a hard time with it when I was learning it, but here we are.